We're going to start taking a look at the last section in this course, and it really has to do with one of the other most fundamental problems in calculus. It's the area problem. Let's say for some reason, let's say we have a nice continuous function, let's say e to the x, and we're looking at the interval from 1 to 2. One of the most fundamental problems in calculus is being able to find the area bound underneath e to the x and the x-axis. So for instance, if I was to graph this, now this is what our function f of x equals e to the x might look like, or would look like approximately. And here's where x is equal to 1, and here's where x is equal to 2. And what we probably would be interested in calculus is we're interested in the area underneath the curve, but bound by the x-axis. Okay? And one of the questions is, well, how can we figure that area out? Well, one way to do that is to be able to use a very basic geometric object to be able to approximate the areas. And we would partition the area under the curve into those basic geometric objects. And one of the most basic geometric objects is a rectangle. And we know that with a rectangle that has a base and a height, the area is equal to the base times the height. So what we could do is we could just divide it up. Okay. Now notice that this would be an approximation, right? And there would be some overestimation here, because what we would be doing is using this point, and obviously this point is 1.5, and the next point will be 2. What if for some reason we wanted a better approximation? Well, what we could do is we could divide it up into even more rectangles. Okay, so check this out. The exact same illustration. So here's our graph. Here's x equal 1, and here's x equal 2. And let's say instead of 2 rectangles, let's use 4 rectangles. All right, and what you'll notice is this time, and these are supposed to be even. And notice this time, there's still some overestimate going on here. All right, but it's not as much. Okay, so this would be n equals 2 rectangles or partitions. This would be n equals 4. All right, and notice that these areas, right, the unshaded region would be the amount of error. So there's less error. Another problem to consider is in both of these, we use the right endpoints. All right, meaning that we started at 1.5, and right here, since we had 4, this would be 1.25, 1.5, 1.75. Right? There's another technique to be able to approximate the area, a basic technique, actually 2 other ones. What if we wanted to use the left endpoint? So the exact same drawing. And again, we have our x equal 1, and we have our x equal 2. But this time, let's use this endpoint. Right? So right here, let's just break it up into 2 rectangles this time. All right. Now this would be the area approximated by the left endpoint. Okay, it should be connected right here and right here. And again, notice that the white space would be the error. So this is a left endpoint. And that's how we can go through and approximate the area under a curve. That's not necessarily a really nice sort of area. Okay, if it was like a rectangle, or if it was a square, even a circle, we could approximate the area. But something like e to the x, or ln of x, or sine of x, or those sorts of functions, we can't necessarily approximate the area. And that's what we're going to do in this section, is we're going to partition, and we're going to go through and just find the areas of a whole bunch of rectangles using this right endpoint method, and also using this left endpoint method. And we're going to break it up into a partition. And based on the endpoints, we're going to be able to find this thing called delta x. Now, delta x is equal to b minus a divided by n. And that's really going to be the base of each of the rectangles. Okay, so this is a common base of the rectangles. Okay, so notice right here, the base from here to here is 0.5, and from here to here is also 0.5. All right, if we were just to say 1.5 minus 1, and then since this is x equals 2, 2 minus 1.5. And so the formula for delta x is b minus a over n, where we're on the interval a to b, and n is the number of rectangles. Okay. And so we're probably going to have to draw some diagrams to be able to do this nicely. And then once we have those diagrams, then we can just go through and use the formula. Right? So we know that this is the base. Okay, well, what is the height? Right? So we need a height of the rectangle, and the height is just going to be f at x sub I. Okay, where x sub I is going to be each of the different left or right endpoints. Okay, so this is x sub I is going to be either a left end point if we're using the left endpoint method, or the right endpoint. Okay, so really when it comes down to it, these problems are just merely calculator problems. They might be tedious, but they're just calculator problems. You might remember similar to Newton's method when we used that earlier. Okay, so notice that we're going to get an underestimate usually for the left end point. Okay, so left end points usually give us an underestimate. And a right end point, as you can see from the diagram above, notice that there's some area above. All right, so right here, this is an overestimate, and right here, this is an overestimate. And similarly, right here, these are all overestimates. Okay, and so usually with a right endpoint, we are going to get an overestimate. Right, so, and basically what we'd like to do is we'd like to be able to add these areas up to be able to get to a sum. All right, and that's what we call the Riemann sum. The Riemann sum is just going to be the approximation of the area. Now, ultimately, okay, and this is going to be a little bit later in chapter 5, but the best area or the best approximation is when we take the limit as n approaches infinity rectangles. All right. And you might remember all the way back from chapter 2, we did infinite limits. So if we could somehow infinitely partition, right, so one last time, here's our diagram. And let's say we could just break this up into really small, like almost an infinite number of rectangles. Okay. We're going to get fewer and fewer errors. All right. So you can clearly see that as we keep getting more and more rectangles, we're just going to get better and better approximations. And eventually, if we were to approach infinity, we would actually get the correct area. All right? And we're going to look at that later in the course when we start talking about something called a fundamental theorem of calculus. All right? So this is just a big overview as to what we're going to be doing in section 5.1, but also what we're going to be doing in the entirety of chapter 5 to be able to approximate and find the areas underneath of curves of both polynomial as well as other sorts of curves.